Here we go. All right. So let's, there we are. And so last up for today, we have Erin Bigelow from here at University of Michigan. So Erin is the research lab manager, and we met Carl this morning. So Erin works with Carl and other collaborators in the Orthopedic Research Laboratory here at University of Michigan. And their usage of Dragonfly, as we heard, goes back to before it was even called Dragonfly. It was in previous incarnations. So they're longtime users who benefited from other Dragonfly evangelists talking about it more than a decade ago. So what we're going to see today from Erin is the use of Pseudo-DXA images for osteoporotic fracture prevention. That sounds very medically relevant. So let's hear it. Thanks, Erin.
All right, so I'm going to just start up front with, this is not just me. This is a really large dedicated team doing this work. So both here at Michigan with the Jepson Lab, other collaborators, Ohio State, University of Colorado, Colorado Springs. So real quick, I'm going to talk about our research interests, but I'm not going to get super into the research aspect because I really kind of want to, with the user group, highlight what we're doing and kind of how we're doing it. As Max said, I'm going to talk about the importance of good segmentation. Some of the analysis tools we've been able to develop within Dragonfly, how we've refined some of those methods, and then some ongoing work. So the problem that we're looking at is fragility fractures, and these are pretty devastating. 1 in 3 women, 1 in 5 men will go on to have a fragility fracture in their lifetime. And they're incredibly expensive. So a 2021 report that was looking just in the US at Medicare recipients, direct cost from an initial fracture was about $22,000. People who had a hip fracture, 30% of those individuals went on to die within 12 months. And very high risk of subsequent fractures, and those subsequent fractures, when they tracked them over 3 years, it was direct cost of $5.25 billion. And that's just in the US, and this is happening worldwide. But what our group is looking at is that we believe that a lot of these are potentially preventable. And you can see here, this is an image of a femur that has already broken, that we did mechanical testing on, and the little skeleton has that circled in red just to kind of orient you. So currently, for someone to get diagnosed with osteoporosis, which is low bone density, they undergo what's called a DXA scan. And this is an example image here. And you can see it's not great. The main indicator you get out of this is bone mineral density. And so that's based on this small rectangular box, and it's a ratio that comes out of there. For osteoporosis, it's diagnosed if your BMD is 2.5 standard deviations lower than a healthy population, which is good to have an indicator. The problem is this diagnosis misses half of people that will go on to fracture. And so we wanted to see if we could take this BMD value, because DXA is widely available, it's low radiation, if instead of throwing that out entirely, could we better understand the underlying structures that create that BMD value so that we might be able to better tailor who's more likely to fracture so that we can work on earlier prevention. So currently with a DXA scan, usually it's, you have a lady who's maybe like 65 years old, they say, hey, we're gonna do a DXA scan. Oh, you've lost a lot of bone, now we'll treat you. And we think that's pretty backwards. We should be able to move that timeline up so that we are preventing more of those fractures. But BMD is just it's a ratio. It's bone mineral content, so the amount of bone in that specific area. And so we want to understand those structures. And so I know we've had some presentations that talk a little bit about trabecular bone and cortical bone. Today I'll talk a little bit more about those. But what we decided to do is we have this nanocomputed tomography system, and we took bones and scanned them both on the DXA and the nano. And this is the exact same bone, so you can see very different information that you're able to get. And quick biology lesson. So cortical bone is what most people think of. It's the exterior bone. It's the bone that's thick. The trabecular bone is these really thin struts and plates on the interior of the bone. So again, what we're trying to do is we have this DXA. We can create something that we're calling a pseudo-DXA with that nano CT image that's the same region as the DXA and get more information out of that. So how we did this is so this is the femoral neck region, so what was in that rectangular box, and we essentially put a ray through at each position. And Carl likes to call it the pseudo detector, but it's the number of bone voxels that you have going through each pixel. So this creates this image in the middle here that's all of the bone, and that's kind of spatially as it goes through there. But then we want to be able to break that out for what is the cortical bone, what's the trabecular bone. These types of bones age differently. They're different strength properties as far as contributions. So the more we can understand about this, the better off we can potentially do some more preventative work. So the first issue we ran into was bone segmentation. We have scans that have air, soft tissue, and bone. So we tried over 20 different segmentation methods, Atsu among them, and they didn't work well. And so we decided to create a neural network and created some ground truth images with, the way we did it was we had 3 different bone researchers each individually look at slices. If 2 out of those 3 individuals agreed that it was bone in the ground truth image. So here's an example of the output of that. And you can see, by and large, it does a very good job. There's a little bit of noise towards kind of like that 4 o'clock area. But when we compared the ground truth images to the output, we had a dice coefficient of 0.967, which we were thrilled with. We did institute a quality check so that once that ran through the network, we had a human look at it real quick and touch up anything. So we removed voxels we thought weren't bone, added stuff in it if it missed it. But again, by and large, it did really well. But the next challenge and the bigger one is the cortical segmentation. So again, we need to identify what's cortical bone and what's not cortical bone. For our images, we had just this femoral neck region was 556 slices. They're large volumes. Manual segmentation is not feasible. It's costly, it takes a lot of time. And the other problem is it can be very subjective. And so what we wanted to try and do is do something that would be a lot faster, would be a lot more objective, and hopefully be able to save us a lot of time as we went through this. So again, we decided to do a neural network for the cortical segmentation. And the big question is, where do you put that cortical boundary, right? Because especially as you age, there's porosity that develops within that cortical bone. And so you can kind of either pick, do you have it where you have very thick bone that's very porous, or do you have a very thin bone on the external and ignore the pores and just count that as cortical bone? So we decided to follow some of the work of the Bell et al. Out of the UK. So you can see the thick line here is kind of where they were drawing the cortical boundary. So now we're going to play a game. Humans are really good at spotting patterns. So where would you draw the boundary on this one? Something like that? Fairly easy, right? How about that one? A little bit more porous. Okay, were you close? And then this one, especially in that 4 o'clock region, we start getting a lot more pores, and they're big pores. Is that where you drew it? How about that one? These are all from the same collection of bones, and so some of those are really easy, right? And then some of them, like this one came up, and our group's just like, do we just walk away? Like, I don't know. But as Max and others have alluded to, consistency in training is the key. So for our first cortical network attempt, we tried to start off with the work of Bell. But then we'd be going through and we'd be like, oh, you know what, this looks like it's thicker cortical bone, we'll add this in. And we kept doing that over and over, and once we trained the network, the output was inconsistent. And we realized it's not a fault of Dragonfly, it was user error. So we went back and we got really, really strict about the rules as far as what we were considering cortical. So we drew these rays from the outside of the bone towards the geometric centroid. And we decided we were going for the thick cortical bone and including all the pores. Because we have a sample that goes from 18 to 98 years old, there's a lot of aging. You have a lot more cortical porosity as people age. And so we wanted to capture that as we were segmenting. So as long as it was a thick bone, or even if there was a big pore, as long as the bone past that was thick and not trabecular-like, we considered it to be cortical. So the dice coefficient for this network compared to our ground truth, once we ran some samples, was 0.98. So I want to show you some examples here. So these are just random bones I pulled out. So you have the initial scan on the left, the bone to background segmentation in the middle, and the cortical segmentation on the right. Just to kind of show you again the range. So there's really different structures, even though like everyone has cortical bone, everyone has trabecular bone. How these look, especially with aging, varies widely. So now we've got stuff segmented, that's great, but we need to actually do some analysis. So we have Rob Goulet, who's our research computing expert. Wave, Rob. Okay. Everyone should have a Rob. But he built 2 custom plugins using Python within Dragonfly, and then also a macro that utilized some of the bone wizard properties. And so we use these to do global bone properties like bone volume fraction, look at properties based on individual slices, and then create our Pseudo-DXA images. So this is an example of one of the femoral necks, and you can see the contribution of all of those bone voxels, but then the cortical and trabecular separated out. And what's cool about this is you get that spatial information is still there, but then in bone, we call them arcades. So there's certain loading patterns, right, that the trabecular really align against. And so being able to see that and how that works, and how also that degrades with aging, can be really important. Like everybody else, we don't have a ton of time, so we wanted to increase our throughput speed. And so we had created 2 macros to batch process the bone volumes. And what was nice about this is it allowed us to get a whole bunch of samples ready, run the neural networks overnight, so that the computers were just running all the time. And then that way we would come in the morning, check the outputs, move them along the next step. So, overall workflow, getting the bones prepped, running them through that bone to background network and checking it, repeating that with the cortical network, creating some various ROIs based on the cortical and the bone, and then running the 3 plugins like I mentioned. But we're researchers, we're not happy with that, even though those outcomes are phenomenal, right? Let's make it better. What we noticed in both networks is that there were very small errors, but where we had small errors, they were consistent. So if there's a pattern, you can fix it. So what we did is we pulled some of the slices that had these errors that we had already corrected and added them to a set of slices we wanted to add back into the network. We also included some slices that had good performance just to kind of boost that training set a bit. And then we went back and created 4 extra networks for both the bone to background and the cortical trabecular. One looking at just adding those additional slices into the network, and then 3 that were totally new models, so new weighting. Bigger patch sizes and batch sizes, as we had gotten some better computers that we could do that with. And then we also, for a couple of them, took the images and rotated them 3 times, so like transformation and flipping them, so that we essentially were able to grow that set of images that the network were seeing. And we ended up, for both the bone to background and the cortical, the specs for model 21 were what ended up doing really well, and we decided to go with those. Dice coefficients for the original and the updated, and truthfully, The dice coefficient is just slightly lower. Again, these are phenomenal networks, but we're actually thinking it's because it was picking up more of the trabecular bone than we had originally put in there. So just some examples of the quality improvement. So like this is one where the circled area in red, it was a couple spots that the initial output missed. The updated network on the right picked those up without us having to touch it. For the cortical network, again, it had issues sometimes where it was really thin bone, which makes sense because the trabecular bone is really thin and it's trained not to pick that up. But the updated network actually did pick it up. And so one thing we wanted to check was when you had the original outputs versus the updated networks, did that change the data, right? And because we were trying to, again, make things faster, we were like, well, the new networks do better. What if instead of being as painstaking with the quality checks, we go through and say, look, if something is a voxel that's highlighted that's truly wrong, we'll erase it. Otherwise, we're not touching it. So if there's some little gaps, we didn't want to deal with it. And it turns out that it really had no impact on our data. So this is bone volume fraction, total area, cortical area, and you can see really, really high correlations. And so for us, this is great because it's a lot less personnel time going into it and still getting really good high quality data. But let's make it better. Everything I showed you was trained on the femoral necks. So we were like, well, we have the whole proximal femur scans, let's try it. And it works beautifully. And so these are largely without any retouching. This is brand new as of Monday, so this is the Pseudo-DXA for the entire femur. And you can really see the loading patterns within this bone here. With our collaborators at OSU, we scanned some distal radii for them. And again, bones that this network was not trained on did really, really well. We also do a lot of mouse work. So this is not this particular network, but if you saw Rob's poster outside, we've been able to do a similar cortical segmentation for mouse bone. We are really hoping to get all three of these networks on an infinite toolbox soon so that anybody who wants to use them can. And so with that, special thanks to ORS, also the P30 Core Center here for funding. And I'm happy to take any questions you guys have.
That's terrific. I can only imagine how hungry the bone community is for community models that you can reuse that separate cortical from trabecular. So
yeah, the cortical trabecular separation, I showed you that in a few minutes. That was probably 2 years of back and forth and what do you consider cortical bone? So a lot of philosophical discussions and then a lot more, I guess, applied discussions as to how do we do this.
Right. Do we have questions from inside the group? Yeah, Benjamin, we'll have to take a...
Yes, did you ever try to use spatial information?
Spatial. So did you ever consider encoding spatial information into your model? And if I may inject a little into that question, you could have your primary image channel, which is basically how much did this pixel attenuate the X-ray. That's what you're fundamentally measuring. If you had done a rough segmentation of this is bone and this is exterior, you could have a spatial model that says this is how deep I am from the exterior. And so now you would have an image channel that is the attenuation and an image channel that is the depth. And you could provide both of those. And for those of you that think I'm just making up the question, Benjamin's nodding. This is the question he's asking. So
if I'm understanding correctly, you're asking if we did this, had that spatial information with the neural networks. We did not include it there. One thing that we did, and I really glossed over the plugins that Rob had put together, when we do the slice analysis plugin, so that goes slice by slice, and it's this huge Excel file that pops out where exactly each bone voxel is slice by slice as you go through. So while we don't have it in the neural networks, we do look at that in the analysis portion of things.
Lots of questions. All right, let's go let's go here.
When you were trying to get that last 10%, which is always the hardest when you're training these models, did you find that the data augmentation kind of helped you achieve or get to more satisfactory results, or increasing the patch size? Which of those two did you think was, I guess, doing more of the heavy lifting in that final 10%?
So the question is, in closing the last 10% of accuracy, do you think data augmentation was a bigger difference maker, or patch size shifting was a bigger difference maker?
Yeah, so probably less than 10%, to be honest. Like it was a very small gap. The patch size helped a lot. I will say I think the data augmentation really helped, and especially when we tried it against some of the other bones that we were looking at, because then you have a network that's seen these structures from different orientations. So part of the issue we had with the first cortical network we did was it really didn't do well unless you had the bone in a very specific orientation. We know from like looking at those proximal femurs, that bone's oriented all over the place, right? So you really need something that's robust and is going to be able to handle that. And I think if I had to guess, my money would be on the data augmentation as being a big heavy lifter on that one.
Yes, in the back.
For the last quiz item that you showed us, how did you determine the ground truth on that? What criteria did you use, or did you not include those in part of the training?
So the question is, what do you do for those samples where we just stare at them dumbly and say there is no difference between where trabecular ends and cortical starts?
Yeah, I will tell you, I'm amazed sometimes when we're looking at these samples that some of these people are walking because the bone is so thin. Like it's amazing. We came back to the really strict rules we had made. So like going from the outside towards the center, is it still thick? Even if it's not thick, if it's the first bone you encounter, we consider that cortical. When it starts really looking trabecularized, we didn't count it. And one thing that we have too, and I didn't really show examples of it, is some of them as they're aging, you might have the original cortical boundary, but then you have this bone remodeling over here. Some of that's pathologic, but all of a sudden you have what was your original cortex that was really thick, starts getting remodeled away, and then you have this real thin bone over here. And so that was another challenge we had to deal with was, well, in that case where you clearly have almost like two cortical boundaries, how do you deal with that? So strict rules and consistency.
A question from Hubert.
Thanks a lot. Can you put the slide 73? Question on the control. Yeah, so see like on the right side, on the yellow, there is background, which is considered as cortical, right? Like on the right side, like it's yellow and it's kind of more transparent, so it's counted as cortical. Can you comment on that?
Did you want to repeat that one?
Oh.
Sorry.
I was too focused visually. Yes, the question is, in the right-hand image, we see some air pixels that appear to be mislabeled as bone pixels. What do you think of that?
Yeah, so one of the things with the plugins that we had developed, and some of them, I will say, like, was pulling some code from some legacy stuff. We did have one ROI that was just cortical bone, and we had a second ROI that was cortical bone and the port, like any cortical porosity. Because especially with aging, we know we have some of those areas that have the big pores. And so the way that we did some of the ROIs, once we had the cortical and the bone, it was just a bunch of Boolean operations to get here's the trabecular, here's trabecular bone, marrow space. We filled those in so that when you went to take like the whole bone volume and subtract out the cortical, you didn't have like weird pockets that were identifying as trabecular bone that were clearly within the cortical bone. So I think this one is probably just one of those that was the cortical all, which would be the cortical bone plus the cortical pores. So.
More questions from inside the room? So Jess, are there any questions from the audience? Okay, so it's pretty late for a live audience in Europe right now, I suppose. I have a question. In your research efforts here, have you been able to rely pretty well on single slice UNet 2D models, or have you experimented or found a difference made by 2.5 dimensional or 3-dimensional models? Is that something you've experimented with here?
Rob?
No, we haven't tried the 2.5 in 3D, but I want to. But the models have been working so well, it's finding the time and going back to create ground truth for the 2.5 and 3D model.
Okay. So the answer is they haven't, the 2D worked so great, why try anything else? But you were worried that maybe you have to paint more ground truth. You can use exactly the same ground truth. You don't have to paint those extra slices to use the 2.5D and 3D models. So I'll show you what I mean later if you want. There's no extra human labor costs. It's just compute cost is a little more expensive and for 2.5D and a lot more expensive for the 3D models if you've tried those. But okay. So let's thank Erin once more and all the speakers from this afternoon.